Okay, so picture this. You have a highly advanced, uh, flawlessly logical robot sitting right across from you.
Right.
It runs purely on math, structured data, you know the drill,
All right.
and you look at it and say, I just love being stuck in bumper-to-bumper traffic for 2 hours.
Oh, I see where this is going.
Yeah, the robot processes this, categorizes the word traffic as a highly positive experience for you, and proceeds to route your GPS through the worst congestion possible every single day.
Because it completely missed the sarcasm.
Exactly. It totally
I
missed
thought,
it. And that massive gap between like strict computation and the messy, fluid reality of human communication, that is the absolute core of natural language processing, or NLP.
it really is. It's the bridge we're constantly trying to build.
Right. So welcome to a special deep dive. We are framing this exploration as the first part of a comprehensive course recap, specifically curated for you, the graduate student learners out there.
Yeah, if you are prepping for your exams or just trying to, synthesize the foundational modules of NLP-like text data processing, classical versus deep learning tasks, vector semantics, this is your roadmap.
We are skipping the syllabus reading and just jumping straight into the mechanics today.
Sounds good. And the best place to start is really with the core scientific and engineering challenge of NLP itself.
Which is ambiguity, right?
Yes, exactly. Human language is inherently ambiguous. It is heavily contextual. It has these complex underlying structures. And I mean, it is deeply tied to subjective meaning.
So to even begin tackling that massive ambiguity, researchers couldn't just, like, swallow the problem whole.
No, not at all.
They had to slice language into distinct layers of understanding. And I know we usually talk about 5 main layers.
We do, yeah.
At the very base, there's the lexical layer, which is just looking at the raw words themselves, right?
Yeah, recognizing that cat and cats are related, just the vocabulary.
Got it.
Once you establish the words, you move up to the syntactic layer. This is the structural grammar. Like, how do nouns and verbs relate to one another in a sentence tree?
But grammar alone doesn't actually give you meaning.
No, it doesn't. Think of that famous linguistic phrase by Noam Chomsky, colorless green ideas sleep furiously.
Right. It's grammatically perfect, but it makes absolutely zero sense.
Precisely. Which brings us to the semantic layer, where we actually attempt to extract the literal meaning of those words and phrases.
And then above that is the discourse layer, right? The one that connects sentences together.
Exactly. So if I say, the dog barked, and the next sentence is, it was hungry, the discourse layer is what figures out that the word, it refers back to the dog.
Oh, okay. And finally, the highest peak of all this, the pragmatic layer.
Yes, the hardest one.
This is the real-world context and, like, speaker intent. This is the layer that understands when I say, can you pass the salt? I'm not asking a yes or no question about your physical capability to lift a salt shaker.
Right, it's a request. And historically, the field of NLP evolved by trying to master these layers one paradigm at a time.
Like the early days, right?
Yeah, in the early days, we relied heavily on rule-based NLP. The philosophy was pretty simple. Language has rules, so let's just program them using handcrafted grammars and templates.
Wait, let me pause you there, because I've actually always wondered about this.
Sure.
Grammar literally is a set of strict rules. I mean, we learn them in grade school. So why couldn't researchers just, hire a building full of linguists, map out every single rule of the English language, and call it a day?
That's a great question.
Like, why did that approach fail so badly?
Well, it comes down to the infinite creativity and, honestly, the sloppiness of human beings. Natural language is just overflowing with exceptions. People use slang. They make grammatical errors that other humans still understand perfectly fine.
Yeah, the context shifts constantly.
Exactly. You simply cannot hand code a rigid template for every possible variation of human expression. When rule-based systems encountered a sentence structure that was outside their program templates, they didn't just struggle, they shattered.
They were brittle.
Very brittle.
Which I guess forced the field to pivot to statistical NLP.
Yes. Instead of writing rules, researchers made the field data-driven. They started feeding these large bodies of text corpora into computers, utilizing classical machine learning and probability.
Just to figure out what words usually appear together.
Basically, yes. It was a massive leap forward. But it still relied on something called sparse symbolic representations, which we will unpack shortly.
Right, because ultimately that limitation gave way to the current era.
Neural NLP, where deep learning and dense vector representations kind of revolutionized everything.
Okay, before we get to the deep learning magic, I want to talk about how we actually get text into a computer in the first place.
Let's do it.
Because computers don't read words. They only read math. So how do we transform a sprawling novel into numbers?
Well, that transformation is the text processing pipeline. And immediately, we run headfirst into a mathematical nightmare known as the curse of dimensionality.
Oh, I love this concept. Let's use the example from the course, Dr. Seuss's Green Eggs and Ham.
A classic.
That book famously uses only 50 unique words. If I want to represent that book mathematically, I could use one-hot encoding.
Right.
So every unique word gets its own dimension or column in a matrix. My matrix has 50 columns. That feels, totally manageable.
It is totally manageable, but a standard English novel might have 100,000 unique words.
Wow.
So if you use one hot encoding there, every single word is a dimension. You suddenly have a matrix with 100,000 columns.
And here's the kicker. Any given sentence in that novel only contains a handful of words. So if I'm representing, say, a 10-word sentence, 10 of those columns have a 1 in them, and the other 99,990 columns are just zeros.
This is what we mean by a sparse matrix.
But wait, why is having a bunch of zeros a problem? Isn't 0 like an easy number for a computer to handle?
You'd think so, but it's a huge problem of scale and memory allocation.
Oh, really?
Yeah, the computer still has to store all those zeros in its memory and perform calculations across them. It's wildly computationally expensive and just terribly inefficient.
Okay, so we need to compress and normalize this data.
Exactly, which is why we run it through a strict pre-processing pipeline. And the foundational step there is tokenization.
Chopping the text into usable pieces, which is usually words.
Usually, yes.
But even that isn't as simple as splitting the text at every space, right?
Yeah,
Like what about New York? Is that one token or two?
good point.
What about the word can't? Is it can and not?
Right, tokenization requires actual linguistic decisions. And once you decide what your tokens are, you typically apply filters.
Like getting rid of useless words.
Stop word removal, yes.
Yeah.
You remove the hypercommon words like and, the or, but words that don't carry much distinct meaning, and you strip out punctuation.
Makes it.
Then we have to handle morphological variations. Study, studying, studies. We want the computer to know those represent the exact same core concept.
So we use stemming or lemmatization for that.
We do.
I always visualize stemming as taking a blunt axe to a tree just to get to the stump. You take the word studying, you literally just chop off the ing, and you're left with studi.
Yeah, exactly.
It's crude. It's not even a real dictionary word, but it quickly lumps similar words into the same bucket.
It is very fast, but yes, very crude. Lemmatization, on the other hand, is the much more sophisticated alternative.
Also,
Well, it utilizes a part of speech tagger, a POS tagger, to determine if a word is functioning as a noun, a verb, or an adjective in that specific sentence.
oh wow.
And then, using a dictionary lookup, it traces the word back to its linguistically valid base form, which is known as its lemma.
So instead of a blunt axe, lemmatization is like carefully pruning the tree using a botanical guide.
That's a great way to put it.
And once we've normalized these words, we want to extract features like chunking, which groups words into phrases, or named entity recognition, and ER, which flags specific people, organizations, or locations.
Right. And once all that linguistic enrichment is done, we can finally build a bag of words model.
Okay, what's that?
It's the simplest way to represent a document mathematically. You literally just treat the document like a bag full of words. You ignore the grammar, you ignore the order, and you just count the frequencies of the words inside.
But raw counting has a fatal flaw, right? Because if the word "the" somehow survived our stop word filter and it appears 500 times, the raw count tells the model it's the most important word in the document.
Which is obviously false.
Right. That's why we use TF-IDF, which stands for Term Frequency Inverse Document Frequency.
Exactly. How would you explain the mechanics of TF-IDF?
Well, I think of it like evaluating someone's hobbies. If someone tells you they like watching TV, that's term frequency. They do it a lot. But almost everyone watches TV. So the inverse document frequency heavily penalizes that hobby because it's too common across the whole population. It tells me nothing unique about that specific person.
Right.
But if they say they like underwater basket weaving, that's incredibly rare across the population. So the IDF score boosts it.
Yes.
TF-IDF mathematically rewards terms that appear frequently in one specific document, but rarely across the entire corpus.
That is a perfect analogy, and this actually brings us to a really critical takeaway for anyone studying NLP.
Which is?
Preprocessing is not merely a cleanup chore, it is a core modeling decision.
Wow. Okay.
The choices you make regarding tokenization, lemmatization, and TF-IDF weighting, they directly dictate the absolute ceiling of your model's downstream performance.
Okay, so we've taken our messy text, cleaned it up, penalized the generic words, and turned it all into math. What do we actually do with it now?
We solve tasks. We might perform sentiment analysis to see if a movie review is positive or negative.
Oh, right.
We might do text clustering, summarization, or knowledge-based question answering. And there is a very sharp divide here between classical NLP and deep learning NLP when tackling these tasks.
Yeah, because in classical NLP, you're relying really heavily on feature engineering,
Highly manual.
right? Like a data scientist might spend weeks running experiments to see if adding POS tags or tweaking the TF-IDF thresholds improves their support vector machine classifier.
Exactly. But in deep learning NLP, neural networks learn those representations automatically.
They just figure it out.
Yeah, you feed in the raw data, and the hidden layers of the network mathematically deduce which features and patterns matter most for the task.
That's incredible.
Yeah.
And regardless of the task, the beating heart behind almost all modern NLP is language modeling, right?
Yes, absolutely.
It sounds broad, but it actually has a very specific definition, assigning probabilities to sequences of words to predict the next token.
Right, because if a model can accurately predict what word comes next in a sequence, it proves that the model has inherently internalized the grammatical structure, the style, and the context of the language.
It actually understands it on some level.
Yes. This prediction engine is the foundation for everything: speech recognition, machine translation, text generation.
Okay, let's look at how we used to do this before neural networks took over. N-grams.
Ah, yes, n-grams.
A unigram is one word. A bigram is two words. A trigram is three. N-gram models estimate the probability of the next word based on a fixed history of previous words. And to do this, they rely on the Markov assumption.
The Markov assumption is basically a mathematical simplification. It assumes that the probability of an upcoming word depends solely on the immediately preceding words, completely ignoring the rest of the book.
So it's like having goldfish memory.
Very much so.
If I'm a bigogram model, I only remember the single word that came right before this exact moment. I have no idea what happened in the previous paragraph. But even with that huge limitation, n-grams run into a massive wall, and it has to do with Zipf's law.
Yes, Zipf's law dictates that the frequency of any word is inversely proportional to its rank in the frequency table.
What does that mean in plain English?
It simply means a tiny handful of words, like the, of, and they make up a massive percentage of all human text. The vast majority of words are actually quite rare.
So why does that break an n-gram model?
Well, because of that massive long tail of rare words, no matter how huge your training data set is, there will be millions of perfectly valid combinations of words that simply never appear in your data.
Oh, I see. So if a trigram model has never explicitly seen the exact sequence Purple Elephant danced, the raw math just assigns it a probability of absolute zero.
Exactly.
Which means the model will never ever predict it, and if it somehow sees it in real life, the math basically crashes.
Right. It's a fatal flaw. So to survive this, we have to use smoothing techniques, the most common being Laplace smoothing.
Oh, Laplace smoothing. I always picture as a mathematical Robin Hood.
I love that.
It goes to the rich, hyper-common phrases and literally steals a tiny microscopic fraction of a percent of their probability.
Right.
And then it redistributes that probability across all the unseen combinations, ensuring that nothing ever hits a true mathematical zero.
Exactly. It ensures stability. We also need to handle words that weren't in the vocabulary at all, mapping them to a special UNK token for unknown words.
Got it. But how do we know if our language model is actually performing well?
Well, we use an intrinsic evaluation metric called perplexity.
Okay, I want to make sure I understand the intuition here. If a lower perplexity score is better, does that literally mean the model is just less surprised or confused by real human text?
That is the exact intuition, yes. You hold back a test data set that the model has never seen.
Okay.
You feed it in, and the model calculates the probability of those sentences occurring. If the model assigns a high probability to the real human text, it means it expected it. Its perplexity is low. It's not surprised.
That makes perfect sense.
But if it assigns low probabilities to actual fluent language, it is highly perplexed.
Now, this is where things get truly profound for me. Predicting the next word based on historical frequency is cool. But earlier we said language is deeply tied to meaning.
It is.
Sparse counting methods like n-grams or bag of words, they don't actually know if two words mean the same thing. They just know how often they appear.
Right. They have no semantic understanding.
So if I want a computer to know that automobile and car are related concepts, How do I teach it semantics?
We turn to the distributional hypothesis. This triggered probably the most significant paradigm shift in modern NLP.
It was formulated by linguist John R. Firth in the 1950s, right? The famous slogan, "You shall judge a word by the company it keeps."
Yes. Distributional similarity argues that you can mathematically infer a word's meaning purely by looking at the context words that frequently surround it.
Can you give an example?
Sure, take
Yeah.
the word bank. If the surrounding words are river, water, and mud, it means one thing.
A riverbank.
Exactly. But if the surrounding words are money, vault, and deposit, it means
Or
another.
a financial institution. The company it keeps defined it.
Exactly. And this realization allowed us to abandon those massive, sparse, one-hot encoded matrices. The ones with 100,000 dimensions full of zeros.
Good riddance to those.
Right. We moved to distributed representations, better known as word embeddings.
So instead of an empty 100,000 dimensional space, we use deep neural networks to compress a word into a dense vector of like maybe 100 or 300 dimensions.
Yeah.
And every single number in that dense vector represents some hidden, continuous semantic property of the word.
Exactly. And the breakthrough model that proved we could train these embeddings efficiently at a massive scale was Word2Vec.
Oh, Word2Vec.
Yeah, Word2Vec uses two main architectures, CBOW and skipgram. Let's break down the mechanics.
All right.
CBOW stands for Continuous Bag of Words. In this architecture, the model takes a sequence of context words and tries to predict the missing target word right in the center.
So it's essentially a game of fill in the blank.
Basically.
The source notes use a great quote for this. The optimist sees the blank and not its thorns. The model processes the vectors for optimist, sees the and not its thorns. It compresses them in a hidden layer and has to guess the blank.
And by doing this across billions of sentences, adjusting its internal math every time it guesses wrong, the vector for the word rose takes shape.
That is so cool. And then skipgram flips the architecture entirely, right?
It does.
So if CBOW is fill in the blank, skipgram is like Jeopardy. Give the model the answer, the target word rose, and it has to predict the context words that likely surround it.
Spot on. And skipgram actually performs better when learning representations for rare words.
Good to know.
But there is a massive computational hurdle here. The output layer of these neural networks uses a softmax function, which has to calculate a probability for every single word in the entire vocabulary.
Oh, wow.
Yeah, if your vocabulary is 1,000,000 words, doing 1,000,000 calculations for every single training step is just impossible.
So they use optimization tricks. What are hierarchical, softmax, and negative sampling?
Well, hierarchical softmax turns the vocabulary into a binary tree. Instead of evaluating 1,000,000 words flatly, the model navigates down a tree structure, making binary choices at each node.
Oh, so it drastically reduces the calculations.
Exactly. From millions down to just a few dozen.
And negative sampling.
Negative sampling changes the task. Instead of asking the network to calculate the exact probability of the correct word against the entire dictionary, it just takes the correct word pair and then randomly samples a small handful of incorrect words.
Like, say, 5 negative samples.
Yeah, and it only updates the weights for those 6 words.
Oh, I get it. It's like a pollster.
Mm-hmm.
Instead of surveying every single person in the country to see who is the most popular, you survey the actual winner and 5 random people just to confirm the winner is more popular than them.
That's a really great way to look at it. It saves an immense amount of compute, and the result of all this training leads to the absolute aha moment of NLP, vector algebra.
Oh, this is where we see proof that the model actually learned meaning.
Yes.
Because if you take the dense vector for the word king, which again is just a string of 300 numbers,
Right.
and you mathematically subtract the vector for man, then you add the vector for woman.
And what happens?
The resulting coordinate in that 300-dimensional space is almost perfectly aligned with the vector for the word queen, king minus man plus woman equals queen.
It really is stunning. It proves the neural network has mathematically mapped out semantic and syntactic relationships. Concepts like gender, royalty, verb tenses, capital cities, they all become literal geometric distances in continuous space.
But our human brains cannot visualize 300 dimensions,
No, definitely not.
which is why we use an algorithm called TSNE, right? It stands for T-distributed stochastic neighbor embedding. How does that help us see it?
Well, TSNE is a dimensionality reduction technique. It mathematically flattens that 300-dimensional space down to just 2 or 3 dimensions. And it does its absolute best to ensure that words that were clustered together in a high-dimensional space remain clustered together in the 2D visualization.
It's like shining a flashlight on a really complex 3D object and just looking at its 2D shadow on the wall. The shadow preserves the rough shape.
Yes, exactly.
When you look at a TSNE plot, you can literally see clusters of car brands in one corner and clusters of emotions in another. It's fascinating.
We have covered a tremendous amount of ground today. For our grad students synthesizing this module, let's trace the arc of what we've unpacked.
Yeah, let's do a quick recap. We started by establishing that NLP bridges human language and computation, facing the monumental challenge of linguistic ambiguity across lexical, syntactic, semantic, discourse, and pragmatic layers.
And we saw the field evolve. Rule-based NLP was precise but incredibly brittle due to exceptions. Statistical NLP shifted the paradigm, making the field data-driven.
We explored why text preprocessing, tokenization, normalization, and TF-IDF is never just a chore, but a core modeling decision that shapes everything downstream.
We contrasted classical NLP, which relies heavily on manual feature engineering, with deep learning NLP, where neural networks learn representations directly from the raw data.
We learned that language modeling, predicting the next token, is the generation, even as it battles the sparsity issues of Zipf's law.
And finally, we saw how the distributional hypothesis revolutionized the field. By replacing sparse, empty matrices with dense, context-aware vector embeddings, we allowed machines to do actual math with human meaning.
It is just a phenomenal journey from raw text to geometric understanding. But as we wrap up this first module, I want to leave you, the listener, with a lingering thought.
Right.
It ties back to the distributional hypothesis. You shall judge a word by the company it keeps. Modern NLP models learn the meaning of words entirely from the context in which humans use them in massive data sets.
Which means the model's understanding of language is a direct reflection of the data distribution it was fed.
Exactly. The math itself is objective, but the associations it learns are inherently human. So when we sit that highly advanced, flawlessly logical robot down and ask it to finally understand us, we have to recognize that the geometric space it builds isn't just a map of language.
No, it's not.
It's a map of our own historical associations, patterns, biases, and contradictions. It's a linguistic mirror, something to ponder as you prepare for your next module. Keep diving deep.